Presentation is by Devinder Sodhi, so spending a lot of years in CREL, doing theoretical and lab works, and also he participated in a few expeditions in the field, different places last year in Svalbard. So then please.
Thank you, Alexei. I appreciate the opportunity to speak here at this workshop, and I'm grateful for the support to attend this workshop. Subject of my talk is mostly about the global ice forces, but how are the global ice forces related to local ice forces? So that's the emphasis of my talk. So the outline of my talk is here. I'm dealing with ice forces on vertical structures. So I denote it by, I denote usually the symbol global with, as a function of time. And its dependence on correlation of local ice forces. And that's the major emphasis of my talk. I will generally deal with effective pressure, or sometimes known as nominal pressure. That means global force divided by the nominal area, which is the width of the structure and the thickness of the ice sheet. I should have included one more bullet point here, that the thesis of my talk is that there are asperities set up that develop during the ice structure interaction, and they come in contact with the structure, and when they are compressed because of the relative motion between ice and the structure, the forces develop, and the fracture has the role to limit that load. That means when the ice eventually leads to crushing of that thing of the ice, it limits the ice loads. So this is the role of fracture. The whole phenomena is associated with fracture of ice, but I will not use fracture toughness in my talk. My beg pardon to John Dempsey and Professor Palmer. I shall talk about 3 sets of small scale indentation tests that I conducted in the lab at CREL, and then I took part in a Joya test, and I shall do the comparison of small scale results with full scale data. I do not have access to much of the data that exists in the industry, but I took part in a GIP and about 10 years ago or 8 years ago, something like that, and I got some full scale data, and now I'm able to compare my small scale results with the full scale data. And I developed a mathematical model for ice structure interaction. My first exposure to ice structure interaction was looking at the ice moving at the Yukon River. This is the bridge pier. There are 6 of them to support the Alyeska pipeline, and then on top of the bridge there is this road. Main purpose of this bridge is to support the Alyeska pipeline. And I was told by the architect, by the engineers who designed these bridge piers, that they designed it for a pressure of 400 psi. That was the thing going in the 1980s. Okay, some more views. Okay, the ice here is freshwater ice. It's 1 meter in thickness, and these bridge piers are 30 feet long and 9 feet wide. That means 3 meters in width and about 10 meters this way. The ice moves at a speed of 2 meters per second. I just happened to clock that, how much time it takes for the ice to travel from here to here, and then I estimated that the speed is about 2 meters per second. So different views looking from the top. The previous picture that I took was from the high spot looking at other bridge piers, and then looking down, then looking sideways, and then looking back. What interested me most was that how an intact ice sheet could just turn into rubble and just be on both sides of the structure, and then also underwater also. I shall talk about Moloch pack data. That Moloch pack at the Amoligat location was deployed in 15 meters of water depth, and all the interaction that I'm going to talk about is that when it was very severe vibration in 1986. As the ice moves against the Moloch pack, it crushes, and sometimes the weight of the crushed ice breaks the ice, and then then this unbroken ice then it comes in contact, and the process repeats itself. And there, I've read some of the reports where they talk about the ice is doing stop and go, because when you observe from the top of the structure looking down, it appears that the ice is basically stop and go, and that's the intermittent ice crushing. And sometimes it doesn't do that, because when it moves at a fast rate, it's just smooth crushing or continuous crushing. This figure was presented by Jeffries and Wright in 1988, and here these data, although the ice load magnitude is not displayed here, but these data were the readings from the from the strain gauges installed on 3 support structures, and they're quite far apart, these A, B, C, and they're random kind of. There is no correlation between the ice forces as measured by these 3 records. And then as this ice flow slowed down, it went into the other mode, which is the phase lock, they call it, or in my terminology, this will be uncorrelated local ice forces, and this will be correlated ice forces. And this thing can be repeated in small scale experiments, except that when I did the experiments, I began from the low end of the speed, went to the high end, and I observed these phenomena, and then again these phenomena at higher speed. Okay, I woke up in the morning today just to relieve myself, but I couldn't go back to sleep, so I started reading on my Kindle. And what I read was it's all depicted here. So this is Plato's Revenge. These are notes from that thing, Politics in the Age of Ecology. What's the forte of human brain? It's the metaphors. What is metaphor? It's a verbal trope or a mathematical formula. Okay, scientific metaphors are self-consciously formal models or theories. So model means likeness. So I'm sort of going towards the model, physical modeling of this thing. But also theories is nothing but it's a show in which the data are woven together to tell a plausible story about reality. So a story can sometimes, I mean, if it is very good theory, then they can do, they will allow very accurate predication. So the task of a science is therefore to find the metaphors that best stand for physical reality. And eventually scientists, the Einstein said that it is a theory which decides what we can observe. So these are the limitations of human brains, by the way. And then again, these notes are from a book by Baker et al. A model is a device which is related to physical system that observations on the model may be used to predict accurately the performance of a physical system in the desired effect. And replica modeling is one of them, that is the same geometry and material as the prototype but scaled in size only. And this has been very effectively used in many other simulations. There are practical limitations, of course. The main one is that you have to validate the results of the replica modeling or any kind of a modeling effort. And I hope that by the end of the talk I will show you some validation of this thing, that is comparison of small scale and full scale measurements. And a system of postulates, data or inferences presented as a mathematical description of an entity or a state of affairs. So that's the mathematical modeling. Okay. In ice mechanics there are two types. Practically everyone follows this fruit scaling because the shipwork gravitational forces are important. So the length scale, you have to make a smaller size model of the prototype. You use the same density, that means water and ice, and same acceleration, because we do not, unless you do it in a centrifuge, we are doing experiments in the same gravitational field as that of Earth. So then the velocity relates by this scale factor, and the pressure and constitutive properties have to be scaled down to conduct the test so that all the forces are in the equal proportion. However, in replica modeling, you scale down and you use the same material as the prototype, but since gravity is no longer important, we don't use these things. Instead, you use the same material. So when you use all the same material, scale factor is simply 1, and the velocity turns out to be 1 also. So that's the benefit of replica modeling, that the pressure that you measure in scale experiments or model tests, they can be directly related to the full scale situation. And you don't have to reduce the constitutive property of the model material. So if I'm dealing with, since I did all my experiments with freshwater ice, so basically I use this replica modeling. Oops. So in my first series of tests, I have this picture shows the experimental setup. So basically I have two plates which are attached to each other by this hinges and bars, and they can rotate with respect to each other, but through these brackets I attach the spring, and underneath the lower plate I attach this indenter plate. So I'm measuring the forces next as they develop right at that ice structure interface, and I can change the stiffness of the whole structure by removing some of those bars in the middle. Okay. At very low speed, 0.6 millimeter per second, the forces rise up, they come down, and then they stay constant. So there is a zone of microcracked ice in front of the indenter during this period here, and this is when the microcrack zone develops, and then eventually it just follows the thing. The carriage is going at a constant speed, but the indenter lags behind because of the force development, and the structure displacement is given over here. So it's all ductile deformation. But at an increased speed of 107 millimeter per second in this case, there is this intermittent crushing, and I use that term because it happened intermittently, not continuously. Later on, at even higher speed, I experienced continuous crushing. But it should be really be called ductile brittle crushing, because during this time Okay, this is the plot of the carriage, and whenever the force develops, the indenter lags behind a little bit, and the slope of this line, is different from the slope of the carriage. That means the rate of indentation is slower than the rate at which the carriage is moving because of the structural compliance. Let's look at it in detail, and so let's start from here. The force carriage and the indenter are together, but as they touch each other, the indenter lags behind and the force develops, structure displaces, and then suddenly there is a finite amount of force that the ice can sustain. So fracture occurs, and then we have this sudden decrease in the force level, and after that the structure moves forward at a very high speed, and then we have this interaction, which I call continuous crushing. For a time, once the structure reaches this portion and it backs up because of the vibration, there is a zero contact, and finally and then the next cycle begins. Now this is the slide where I show that this is one time that I got structural vibration at its natural frequency. So carriage moves over here, indenter displacement is indicated by this curve. You can notice that whenever the indenter slows down, there is a rise in the force, and this is totally in concert at all times. I relate this incident to the swinging of a child by being pushed by the parent. As soon as the child is about to go back, then you get a push. So this is the push that you get every time, and if you can admit, this morning I talked with Andre, saying whether the pushing of the child is that a forced vibration. He agreed. But when I said that then he should agree also that this kind of a situation is also a forced vibration situation. But anyway, we can talk more about that later. And in one experiment, I was incrementing the speed of interaction of the carriage, and one time, suddenly the interaction changed from this intermittent to continuous crushing. And why should this happen was asked by Professor Morel in 1989 when I made this first presentation, that these low force values are otherwise very puzzling. He gave some explanation that there may be some melting taking place and things like that, but if you can go back, so from this force level you get this force level. Okay, I have given the forces as measured in kilonewton, but then in effective pressure terms, this is like 2 megapascal, and here it is more than about 10 megapascal. So there's a tremendous difference. Why this happens at that time I could not explain, but now I hope to explain all these things to you. So at the end of the test series, I made a failure map that if the relative speed between the ice and the structure is low, there will be creep indentation for narrow structures and creep buckling for wide structures, because creep buckling is also a competing mechanism. At very high speed, you'll have continuous brittle crushing taking place with very small amplitude of vibration. However, in the middle, there is alternating ductile brittle crushing of ice, causing very vibrations of large amplitude, and this sometimes gets the compliant structure into trouble because of this type of ice failure. So what I did, I plotted all the data that I had from my test, plotted with respect to the indentation speed. That means the actual indentation rate the indenter is indenting into the ice versus effective pressure. And so I published this figure, and Blanchet in 1998, he put his own data points from the measurement that he had made, and I was somewhat happy to see that this C, that means continuous crushing, is close to the full scale data. I never expected that to happen, but I was really encouraged to work more on this topic. Then my second set of experiments is with segmented indenter, and I have 7 of them here. It's the same setup as before, except that each segment is in the form of a T, and it is supported. Each segment is supported by 3 load cells. So when it interacts with the ice, the local ice forces are measured, say in this segment, completely independent of the one of all the other segments. Before I go on to discussing the results of this particular set of experiments, let me talk about correlation functions. There are 2 correlation functions that have been published in the ice mechanics literature. One is by Cry in 1978 and Ashby et al. In 86, and by Dunwoody in 1991. Both these functions give you eventually the same conclusions, main conclusion. So let's say that here the delta or L that is discussed here, these are correlation length parameter. That means within this length everything is correlated. Outside this there is no correlation. But you can also express that, okay, there is the negative exponential decay on this side and this side, there will be some correlation here, but anyway, this is an alternate way of doing that. I will discuss the one over here right now. Let's say that this is the width of the structure, W, which is divided into n segments. N can be arbitrary. This is something to do with the asperities that are created as a result of ice structure interaction, and it is believed to be somewhat related to speed of interaction. So the global force is equal to the sum of all the local force. That means all the forces measured in each segment is depicted here. F sub I goes from 1 to n. So effective pressure P sub T is divided by the nominal area, and you can write down in terms of this n delta is simply width. So this is the effective pressure in each segment. So it is simply an average of all the effective pressures. So P of T is the global P of T is the average of all the effective pressures in each segment. And from statistics, this is basic statistics, by the way. So the average of P of T, or the global effective pressure, is simply averages of the pressures, local pressures in each segment divided by n, or average of the. So this relationship exists simply because of statistics. And if we assume that mu sub I is equal to mu, then the global effective average of the global effective pressure is simply equal to the local average, and this will be displayed in the data to follow later on. And next thing is that we have to worry about the variance of the global effective pressure, and that is given by this expression over here. let's not go into the detail, but basically say that the sigma ij is either the variance, if that happens to be on the diagonal, or covariance in this matrix here. And assuming that all these values are equal to sigma, then if the forces are totally correlated, then the standard deviation of global effective pressure is the same as the local standard deviation. However, if they are totally uncorrelated, that means outside the segment there is no correlation, then only the diagonal gets populated and these ones are all zeros, then you get the standard deviation of global effective pressure as the standard deviation of the local pressure divided by square root of n. So there is a decrease in that, and this is the same thing like if you invest money in a mutual fund, you have smaller risk. However, if you so another thing is that if you put n is equal to 1, that means there is a correlation across the whole width of the structure, then you get this result over here. So if you have less number of stocks in your mutual fund, then there will be high variability. It's as simple as that. And so let's look at what the data is telling us. This is a very busy slide, but I wanted to put these data all together. This is the data in each segment, 5 segments here, and this is the total force. And this is the total force is obtained by simply summing up the force in each segment at each instant in time. And these data are from 8 millimeter indentation rate or the carriage rate, and these data are from 101 millimeter per second, and these data are 400 millimeter per second. Please notice that there is perfect correlation of forces at low speed indentation. And let's look at this one. Anyway, visually there doesn't seem to be any correlation between the segment force measured and the total force. And in between there is some correlation at times, but not a whole lot. So now this is the data. I'm plotting here the minimum and maximum and the average in each segment and the global load. Notice that even though there is a perfect correlation of data, the global average is the same as the local average. At the intermediate speed, the variations are still very large compared to the global variation, but the average is the same. And then at very high speed, average is the same, and these variations are much bigger than the one for the global force. This is the distribution for the low speed data. There are 2 sets here. The pink one is logarithm of the pressure, but anyway, just look at the blue shaded area, and this is the distribution as recorded from the test. And this is the distribution, more or less has a little tail over here, but more or less not much different from that the previous slide. And then in the high speed data, it's almost normally distributed around the mean. And this is the covariance matrix of the low speed. Pretty much the whole covariance matrix is populated, and when you increase the speed, the diagonals remain high, but the other covariance terms go down. And then at very high speed, only the diagonal elements remain. That means there is no correlation from segment to segment. So just to check on the main point, indentation speed affects the correlation of local ice forces. And the average of global effective pressure is approximately the same as those in 5 segments during both low speed and high speed tests. During a low speed test, the minimum and maximum of global effective pressure is approximately the same as those in the segments. And during a high speed test, the difference between minimum and maximum of the global effective pressure is less than those in each of the 5 segments. Histogram of the global effective pressure for high speed test indicates a normal distribution about an average value. Correlation of local ice forces is expressed in terms of a length parameter, either delta or L, which decreases with speed in with increase in ice speed. Oops. And if you want to have any interest in getting the maximum estimation of maximum global effective pressure, then this can only be done for the case of high speed indentation test, because it has a normal distribution, and then we can say that okay, the maximum value of global effective pressure is equal to the average plus 3 times the standard deviation. And if we take out the average outside this thing and look at this term here, as the structure gets wide, if the number of asperities per unit thickness length increase, then this factor goes down and we are left with this thing here. So for very wide structure, I propose that the average value of the global effective pressure is a fundamental property of this process. And if you measure this thing over a very limited area, that's the local ice pressure, and it can be equated to the whole wide structure. However, the variation of a locally measured force will be higher than for the wide structure. And if we can estimate the size of the correlation length parameter, then we can estimate that okay, how big this factor should be in comparison to the average value. So this is nothing but the coefficient of variation about the mean, and it can be 5%, 10%, and estimates can be made. Okay, moving on to the third in chronological order, and I took part in the Joya test from 97 onward or 98 onward, so only 3 years of my participation with them. So this is the experimental setup. They need a crane to set it up, very expensive set of equipment, and they lower it. They make ice fresh. I mean, every time they need an experiment, so they clear out the ice and they grow the ice, and then they cut out the ice and then put the structure down. And so the structure is still above water, but it is segmented. Each segment is 10 centimeters wide, and it is 15 of them, so that makes the whole width of the structure is 1.5 meters. Thickness of the ice sheet in these cases are 10 to 15 centimeters. And then on top of this thing, we attached this tactile sensor. This is a useful device if you have something at the back to measure the total force, because in order to calibrate the readings from these from the tactile sensor, you need to have the total force from the tactile sensor and equate it at that particular time with the measured forces from those load cells, and then you can sort of say that okay, that's the total load. And so this is the kind of a plot of the pressure along a line-like failure and at 30 millimeter per second speed. And after this test, we conducted another test at 0.3 millimeter per second and 2 orders of difference in speed, and it was already, the ice sheet was already pointed at, it was like line-like contact, but it decided that okay, it doesn't want to fracture anymore, so it started to spread across the thickness. And I have a oops. So this is the line-like contact. This is okay. After the test, somehow this thing is behaving in a different way than I expected. Okay, now, okay. So this is the video from the time when the contact was expanding vertically up. Maybe I should, okay, there it's moving. Okay, let me get back to this thing again. There is now. Okay. Okay, that's the. See, the pressure is not constant at any time. These asperities develop at different places, but along a line basically. And something just falls off and then goes away, that's going down. Okay, let me proceed to the, so this I have already shown you. Then when I came back from Japan in '99, I had another set of experiments at shoestring budget, partly supported by my lab, partly supported by ExxonMobil. And in this case, I had this 146 millimeter wide structure, but then the tactile sensor area was 84 millimeter wide, and this is the ice sheet here. Okay, this is a low speed test, and as the contact area is, oops, I have to press this thing too. If you notice that as the contact area is increasing, this is all ductile deformation of ice, creeping basically, and the thing to note is that even though the contact area is increasing, this is almost linear with respect to time. That means with respect to the displacement. So this is one kind of a deformation, and the next kind of a deformation is at very high speed, at 502 millimeter per second. I hope I can. Now, even though we were scanning this thing at 137 hertz, it was not fast enough to record what was happening in between two frames. So what you see is that asperities developing, dying down, or they don't exist anymore because the indenter is moving fast enough, and each asperity is broken up by the fracturing process. And so what we have is the contact area shifting from place to place. Okay, then the intermediate case, 54 millimeter per second. The actual indentation rate varies in two orders of magnitude. What I mean by that is that during the time that the loading takes place and the loading is described over here. It is 7.8 millimeter per second, but during this time, when the fracture takes place at this time, the structure moves back at a very high speed, and the speed from this curve here is about 700 millimeter per second. So 2 orders of magnitude difference, and so the length of time that it takes is very small compared to this time, but the amount of displaced indentation is small, whereas over, the length of indentation is very large over here. And let's see what. So the structure is not in contact with the ice, and now the contact is made, and these asperities are the remnants of the previous cycle, and they stay there and they expand in area. So this, I will call it correlated ice forces, local ice forces, and then they move very fast. These are uncorrelated ice forces. So there is another cycle coming up, no contact, and then they are coming up, and so these are the remnants when the ice moves forward, and then these grow in area. But notice that this is linear with respect to time, and I will speak about that a little bit later. Okay, oops. And this is the correlation length parameter, this is the correlation coefficient from the slow test. That means it doesn't change with respect to this distance x, whereas high speed test, that's the curve, and the best fit, approximately best fit curve is given by this. So I had to choose a parameter here that I chose that 4 millimeters. This is about 1/10 of the ice thickness. Now comes the thing about, so how can we estimate, when the failure will take place because of correlated ice forces. So here this is a picture shown that all the pressures, and this is from, by the way, Yuka Thukri's thesis in '96, and he proposed that if the pressure P is related to this A, and this is the formula. So there is this what you call the fracture toughness, and I estimated that the fracture toughness is, or he actually estimated the fracture toughness is between this thing for freshwater ice, and this formula can be changed to nominal pressure PA divided by H, and then this is simply a geometrical factor. So it shows that okay, if we assume LEFM, it's a h to the power minus half. And in '99 we also I was here in Cambridge, and we published a paper, and it showed that okay, the relationship of P nominal with respect to the ice thickness should be h to the power minus half. And when I plotted the small scale test, which is from freshwater ice, and this is the Molik pack data with almost more than 2 meters in ice thickness, then the best fit curve has a slope of minus 0.4, and if I force the slope of the curve to be minus half, then it's given by this dotted line here. And I showed it to John, and he agreed with me that okay, 0.4 is a better choice. And now we come to the second, this high speed test data. That means when the structure is moving at speeds greater than 100 millimeter per second and large aspect ratio. So all the small scale data satisfying this kind of a condition are plotted over here, and then the Molik pack data where I could verify that it was continuous crushing is plotted here, and it's plotted with respect to ice thickness, and for, I mean, there's a lot of scatter in both sets of data, but more or less it is not affected by the thickness. So in this case, this is affected by the scale effect, and in this case it is not affected by scale effect. So there is two sets of processes and two different things, so do not compare one with the other. When you do that, then the scale effect is no longer there, whereas in this case it is there. Okay, I should finish soon. I did a mathematical model, eye speed. In this model you need to specify eye speed, thickness, width of the structure, structural parameters m, k and psi. This is the damping coefficient. So the only three things you require of the about the ice is that the effective pressure to fail in fracture, that is the, when you have intermittent crushing, and then the effective pressure when we have continuous brittle crushing. And then these models have been described, I mean, I've published this thing, just that I've improved the model a little bit, and I've included this elastic and the viscoelastic part, and I'm going to go into this. So I assume that each asperity is in the form of a sphere, and I have the elastic formula for these this kind of indentation, courtesy of Hertz, and I convert those formula. I didn't do this conversion, but anyway, there is a it is possible to convert these formulas into viscoelastic formula. So these are taken from Johnson book, Hertzian contact formula. And what we do is that I assume that ice behaves like viscoelastically. So here's the elastic part, viscoelastic part, and there's a relaxation time tau. It's a very simple model, but I just wanted to see what happens in the simple model. So if the relaxation modulus function is given here, and then the compliance function is given over here. So what you do is that you take the 2g, replace it with this formula or relaxation modulus function, and then do a convolution integral as shown over here. And when you do all this math, you come up with this integral over here, which is non-dimensional. So the rest of the terms can be put together here with a non-dimensional value, and then this is the value of the non-dimensional integral, and I just instead of taking this little bit of nonlinear thing as a linear, and then this function can be related as a simple spring. The main thing is that this t over tau can also be taken as indentation into the ice. One thing to notice is that this relative speed at which you indent varies at 3/2. Suppose the relative speed changes by 2 orders of magnitude, which I found in my test, then this factor here changes by 1,000 times. So in other words, when you're moving very fast, these asperities are crushed very, very quickly. They don't have time to survive, whereas when you're moving slowly, they have time to survive. They can correlate with each other. And so I took an empirical definition of k sub I, and doing this thing, I have the loading phase, extrusion phase, and separation phase. All of this thing can be written down or explained in great detail if I have time. And then the sudden change in acceleration is depicted here. That is before the fracture taking place, it is this formula, but after the fracture, immediately after that, it is this formula here. And because of the compatibility of displacement and speed, these two terms are 0, so the change in acceleration is given by this formula here. And then if the structure is very compliant, I just choose this loading, extrusion, separation. But if the structure is very rigid, not so compliant, I just choose this kind of a version. So this just shows, you know, what are the conditions when it changes from one set of phase to the next set of phase and things like that. For instance, here when the ice force is greater than force, you go to the next phase, and when the relative speed is 0, then you go to the next one and then keep on going. So doing all these things, here's the comparison of my model, numerical and results which are given over here with actual test data. One thing I don't have in my model is that, you know, these peaks are not of the same value, whereas in my model they are of the same magnitude. That can be fixed by simply changing something. Here is this another set of tests at a lower compliance, and I can reproduce these results. I tried to reproduce these results from Molik pack data. I could not, because my model simply assumes that this is constant. But if I put some variation of this force here, then I may be able to reproduce these results. However, when I go to the next series, I mean, the speed is 100 millimeter, this is 0.1. So this is about 10 millimeter per second. Thickness is 2.4 meters. Structure width is 80 meters. And these are some of the other parameters that I assumed in my simulation. So the measured are in brown and simulated is in blue. So I tried to simulate these two things over here, which comes out pretty nicely, except that I have a constant, the blue ones are simply constant speed results. That's why as the flow slows down, it goes out of sync over here. And then this is the acceleration plot. Again, it works very well over here. And then this is the phase plot of a stable cycle. And so you compress the ice. When it fails, it goes very fast. Over here you change this thing, and then so this is only two phase, like loading and then extrusion. So this is my attempt to understand ice crushing during ice structure interaction and to relate the results of small scale tests with and medium scale test data to the data from full scale measurements. It is the correlation of local ice forces at low and high speeds of indentation that give rise to intermittent and continuous crushing of ice during ice structure interaction. Thank you for your attention.
So Dev, how did you get the relaxation times? Were they just kind of tuned to fit, or is there a physical basis for that?
I tried to measure the relaxation time by pushing the indenter into the ice and then waiting there and recording how the ice relaxes. I was not totally successful in doing that, but it is in terms of minutes or hours maybe, I don't know. I don't have any idea. I could use some help in doing that. I have the data of those tests, but not fully analyzed. So as long as it is more than minute, here we are talking in milliseconds or a fraction of a second of the loading. So as long as we are on a very short time, so I think that my solution that I have of converting from Hertzian contact to viscoelastic contact is applicable for a very short period of time.
Yeah, I mean, that's a nice feature of it, that you'll accommodate that deformation. There's probably more elaborate ways to do that and get the time dependencies a little more
Yeah.
physically based, but
Yeah.
I think it's a really key feature
Yeah.
that gets at the rate effects. You
Yeah.
could probably tune up the calculations, because I think there's going to be more than one relaxation process.
You see, all I was interested in showing us that it's a linear relationship, not a non-linear, very complicated relationship. So once I assume that it is linear relationship, so by changing the modulus of elasticity, and there is another parameter called beta, so I can tune in the rate of rise of the forces. And then there is a cutoff time, cutoff thing because of the fracture process, and it goes up to that. So the loading is only because of the deformation of these asperities, and then sudden drop after that.
It's possible, I just want to extend it, because relaxation time probably depends on temperature. Did you observe something in field conditions that this range of lock-in or depend on temperature, so then it's quick, because it's warmer, so relaxation time is shorter. So then you may get some synchronization for smaller speed of ice drift.
Yeah. The results that I showed you for relaxation time equal to 4, the time equal to the 4 times the relaxation, all I'm interested is in a very short domain, because we are talking in milliseconds, whereas relaxation time is very big. But in terms of temperature, all my tests were done with ice sheets ranging from, say, 20 to 40 or even 45 millimeter per second, and eventually when I went to greater thicknesses, I broke the test apparatus simply fell down into the water. So that was the end of the series. So all my tests are done between the range of 20 to 40 millimeter per second. Millimeter thickness. Yeah.
Very nice presentation. I just wondering if you have looked at the same model in the context of the Joya data and how the parameters change when you have sort of warm saline ice.
Yeah. Joya data is there, but oops, the blue dots over here relates to the Joya data. It's a very warm saline ice, and I only considered those tests where it was continuous crushing, and so these are the values. They're much lower than those values.
But did you look at applying your model to these data, or?
No, I haven't done that, but I have the data. Unfortunately, it's just that I haven't done that part. Yeah, there is a test that was done in front of all the spectators, I think February 4, 99. I think if you want to try that, that would be the test, because ice was brittle. Yeah, there is something that I forgot to mention, that one of the key feature of model ice that one should have is the brittleness, and that's only possible with freshwater ice. So when it is missing, then it is totally a different thing.
Thank you very much. Is it right your model is one-dimensional and linear?
One-dimensional? Yes, it is one-dimensional. Yes. Yeah,
So in
single
your
degree of
model,
freedom.
the distribution of pressure
Yes.
across the contact area, like in metaking model, is not important. You do not.
Say, I don't understand the question.
Distribution of pressure
Mhm.
along the contact area is not included
Yeah.
in the model.
I'm assuming that whatever is happening is uniform across the whole thickness. Yes.
Okay.
Can't carry all the books, actually.
Just a short question. So then this, your contact area is, I assume that one spot of high pressure over the ice thickness. Is it because you showed just you have only, you cannot have two places of stress concentration over the ice thickness, and it is based on your data that.
No, this spherical model is simply for convenience because I have the elastic results.
Yeah.
But then I apply a rigid wall moving into that
Yeah.
asperity. What will happen? So this is only just to justify that my linear relationship with respect to time or indentation is justified. So,
Because
but
spherical. You ask about, you
Yeah,
said
uniform.
about plane,
Uniform.
but you use spherical asperity.
no, spherical at one spot
Yeah.
in the ice sheet. I mean, these are several spots on the
Yeah.
across the ice thickness,
Then,
and they appear and disappear at different times. It's quite random.
so then previous question was, discussion.
Yeah, what
This-
what I mean is that these asperities are uniformly distributed across the whole width of the structure, and then they appear and disappear, and they do not. They may occur at the same time. That means correlation is there when the speed is small, but the correlation disappears when speed is very high.
But if you count viscosity, so then you have more time for correlation.
Yes, that's right, exactly.
So then, therefore, it is important.
Yeah, that's right, exactly. Yeah, you have to take that into account. Otherwise,
You distribute them is in the cell like of the same size,
yeah,
like square shaped cells
Yeah.
over the all contour.
that's right, exactly, yeah. And the n or the correlation length parameter that changes with speed. So you can call it, so if they are all correlated, you can say that n is equal to 1.
Mhm.
If they are not correlated, n is larger than 1. Yeah.
And do you have in Andrei model this correlation function between different segments? Or
First, I would like to comment that it's highest model and not
yeah,
Andre's.
the highest model, yes.
Which model, sorry?
One which we presented.
Oh,
I can, yeah. Yeah.
And the correlation comes through the vibration of the structure. All the forces.
Okay, but you introduce correlation using
Yeah.
like the data.
that's right.
Yeah.
And correlation occurs only at low speed, and there is no vibration during the life of a of loading time. There is hardly any vibration that I found in my experimental results. So, so basically, it's just a uniform compression, which is gradual, and then all of a sudden, there is fracture, and then the structure advances fast, and there is a different type of ice breakage, and this results in like breaking of all these asperities non-simultaneously.
So then, thank you.
Thank you.